Can you see my screen?
Yes, sir.
Okay, so someone please start WhatsApp group to so that we can interact easily. So whatever this lecture notes, no, so whatever.
Okay,
Yes.
okay, sir. Please share your WhatsApp number, sir, so that we
Okay.
can add you.
988 988 444.
Okay, sir. Wait, wait.
I'll just write it. So 988.
988.
42476. It's there on the screen. Just keep it. Okay, shall we start? All are there? And 11. Yeah, I think all are there. Yeah. So we'll discuss today a little bit about fluid properties. Okay, so last class we were discussing about this fluid properties. So one is the density thing that you have seen. So the second one is this viscosity. Viscosity. So crude definition is basically you give internal friction. Okay. So whatever fluid offers some resistance to the shear stress, you give the shear stress, it starts moving. No, that is the fluid definition. So whatever, however small it is, for which there is a resistance. Okay. So it's a property of the fluid. Okay. The property of the fluid that gives resistance to shear stress. What is shear stress? You don't worry. See, we are talking a little bit, physics ways, physics here. Little bit of this fluid properties appears to be physics. You don't worry, but you should have in mind what is going on with the fluids. Okay. So the property of the fluid that gives the resistance to the uses crudely that internal friction. Okay. This is basically internal friction. This is what we define, no? Isn't it? But if you see, this is not the correct, this may not be the proper one. So a proper one usually in some other textbooks, actually this is the correct one, some sense, because other textbooks, they may give usually for Newtonian fluids. Okay. So usually when you define this viscosity, they give for Newtonian fluids definition in some textbooks. So that for Newtonian fluids, they usually what they give we write. Okay. What is Newtonian fluid? We'll find out. Okay. Newtonian fluids. For Newtonian fluids, this definition is, so definition looks like this. So generally, that is a law of Newton's law of basically Newton's law of viscosity. Okay, Newton's law of viscosity. So what it says is shear stress is directly proportional to viscosity. Once we know that the fluid is with some deformation, okay, with some rate of angular deformation. What is the meaning of this? See, you generally give some shear stress, right? So you just push it a little bit, okay? So in the horizontal directions, you give a force. That is what is shear stress, right? Once you give, you know that it's a fluid actually starting. What is the meaning of fluid flowing? It's basically deforming, right? So the deformation, whatever small piece you consider initially, if it deforms, no? So if it deforms like this, that is what is the deformation. So angular deformation, the rate of angular. So in a unit time, what is the rate of angular deformation? Okay. So it was initially like this. This piece is becoming this one. So that angle, that angle theta, no? Theta into this one. So that what is the change in the velocity divided by this length? That is what is actually, we will see that is actually angular deformation. Okay. Have you followed any question here? So once you have that
Yes,
angular
sir.
rate, so once you apply the shear stress, basically this is the rate of angular deformation. Okay, so if there is angular deformation rate, so shear stress is actually proportional to the viscosity. So for Newtonian fluids, basically this goes linearly. So this is a constant. Okay. For non-Newtonian fluids, like this is actually good for non-Newtonian fluids. Non-Newtonian, it's a crude one, first kind of principle. Non-Newtonian fluids like tar, some oily substance. Okay, so some what else you have? Some molasses. Molasses at certain temperatures, at colder temperatures. Okay, not so hot. At not so hot. So all these things, in non-Newtonian fluids, basically it won't be constant. Viscosity won't be constant. So non-Newtonian fluids, Newton law of viscosity tells you that it's basically shear stress. Let's call this shear stress. That means some kind of force per unit area. Okay, is actually proportional to the viscosity. So we explain this Newton law of viscosity through an example. Okay, let me give you that example. So you have basically two plates are here. So this is one plate. Okay, let me draw this. This is one plate. This is the plate you have, and you also have another plate here. Between these two plates, you have a fluid. Okay, so initially, let's say A. So A is here. So A is here, and this is B. This is C, and this is D. So this is your fluid element. Okay, are you there? 1 minute.
Yes, sir.
Because there is some sound. Okay, fine. Somebody else wants to join. Who is he? SK Emmanuel, PhD. Eh? So okay. So this is a small piece. Let us say this is your fluid inside. Okay. So ABCD is the fluid, and this is of length. Let us say H. H is the length. Okay. The length of the channel you can imagine. So there is a fluid moving in this. It's not moving. So there's the fluid inside this. So let's consider this element ABCD as your fluid. Okay. So what I do is I apply a force. Okay, some force I apply along this horizontal direction, and I move this plate with the velocity u, constant velocity. Okay, so So when you do that, so let's consider this as the x direction, and you consider this as y direction. Okay, this is your y direction. So x direction, y direction. Now you have so ABCD is an element. So what you do is in the this when you consider this viscosity, this element, you look at this is moving, right? So this plate is moving, so the fluid here actually will go at higher speed than the bottom. So when it comes to the bottom here, actually that is called no slip. So when you consider for viscous fluids, this because of the bottom structures are there, no solid. This is our solid piece, right? The channel. The solid is so rough. For real fluids that is the case. Okay, if you actually microscopically you look at it, solid is kind of some kind of rough surface like this. It will be there if you look closely. Any smooth solid surface may be looking like this. So the fluid once to here, no, so it molecular level, it enters here and try to get the same zero temperature here. So that's called no slip condition. Okay, the velocity here will be zero. Okay, so it's only moving in the x direction, the velocity. So let's call this u. U is that fluid velocity. Okay, so u is the fluid velocity. Fluid velocity at xy, at any point xy. Okay, so at the bottom it will be usually zero. So that is called no slip condition. So u is equal to zero at a. So a or d. Okay, so this is called ABCD, right? So this we put small d. This is no slip condition. No slip condition for viscous fluids. It won't be the case. For example, you will not see that. So it is actually moving. If it is not viscous fluid, that is ideal fluids. Usually you don't take this u equal to zero. So u is simply flowing whatever the velocity, whatever velocity inside. No, that will go with that. Okay, so it won't stick. Basically, it's not sticking. If you see the like that, so ABCD element, once it goes with the speed of u with some force, okay, you applied the force and you allow this upper plate moving at the speed u, this deforms. Okay, it starts moving. So when it starts moving, this piece will become like this. Why is it like this? Because this is your this is now your fluid. Okay, this one. So it moves because at the bottom there's no slip condition. That's why it won't change. Here it won't change. Only at the top it will go little further, and as it comes down slowly, it reduces its movement. Okay, so it goes like this is your new. After some time, this is what you see. Okay, in the unit time, let us say. Okay, so experiments suggest that this force that you apply, no, that force is actually proportional to the area of the plate. Okay, so A, where A is area of the plate. You need to apply more force, right? If you want to apply, if your area is big, you have to apply more force. So that's what is the meaning. And then it also, if you need more force to get more velocity also. So it is also proportional to A and U, and it is actually inversely proportional to the distance between these two plates. Okay, that is what is H. So if you do this one, so this is by experiments. So when you do this, what you get is basically F equal to some constant. So that constant is actually your viscosity. So this is A U by H. So this particular situation, we are trying to give you the meaning of viscosity using this small setup. We're trying to explain what is this one. So we know that shear stress or normal stress are basically it's a force per unit area. So you have a fluid element and you want to have a pressure. Now, what is the pressure here? Pressure is basically the force per unit area in the normal direction. perpendicular. Okay, so this is exactly a normal. This is like a normal, right? So at normal direction, at this on the surface, area is the area of the surface here. On the surface, unit area, if you see exactly what is the force acted by the outside fluid on this fluid element, that is exactly normal stress. If it is horizontal way, if you apply, so that is your other component. So that is your shear stress. Okay. So F by A, you can write F by A as mu U by H. So this implies F by A is basically that one. So F by A, but we are only applying here in the horizontally. That is why you say that is it is your tau, shear stress. Okay, shear stress tau. Let's call this tau. Shear stress is tau, which is equal to mu times U by H. Okay. So what is U by H? If you actually see U by H, U is, what is U by H? So U is the, with that force you change of the fluid. Fluid is going. Fluid here, a BC fluid. What is the velocity of BC? 0 initially, and then it goes from, let us say, B star, C star. This is your C star. Okay, B star, C star. So B star, C star velocity is U. So that B star, C star velocity is U, and that divided by H is actually your rate of deformation. Okay, so that's basically rate of angular deformation. So it's angular, no? So it's going like you know, fix one point. You take a string, for example, you take a string. Okay, this is the fixed point. Now you try to move with some theta. So this velocity, you go from this, you know, that is your angular velocity. So the if you are moving in a circular way, the velocity of this particle as it move with theta, that is your angular velocity. So here the velocity is rate, no, the rate at which this is the deformation. Is actually velocity is changing, right? So here it's 0, and here it is U, capital U. So velocity means the deformation divided by time. So that's why we say that rate of angular deformation. Followed? So you have the angular deformation. So U by H is basically rate of angular deformation or rate of strain. Okay. So or you say that is basically rate of strain. Deformation is basically, you can view it as quantitatively, it is a strain. So what is the meaning of deformation? Deformation is like, you know, qualitatively you tell that whether some piece is deformed or not. Okay. This is deformation. So what is strain? What is the strain means? Strain is basically a quality. This is quantitative, qualitative deformation, qualitative way. So if you say quantitatively, so exactly what is the amount that you, if you are asking, this goes to this type of deformation. What exactly? What is the change? Okay. So rate of change. So that is what is exactly. So strain means the change, exactly the qualitative. So this is the qualitative. Strain means, strain is basically qualitatively, quantitatively you tell the deformation. Okay, that is quantity of deformation. In unit time, let us think. So that is the meaning of deformation and strain. So this is a kind of the you quantify it. That is what is the rate of strain, because you are dealing not with the shape here. For example, x, no, x direction. You're not talking about x, no. So you're talking about the its velocity. Rate of change of that displacement x divided by time is 0. So that is why you say that is the rate of angular deformation. Okay. So angular comes because of the h. Okay, so that distance. So that's what is rate of strain. This is basically rate of strain. So if it is a rate of strain, and you can also say that U by H is basically in terms of that velocity of the fluid. If you actually see that one, that picture again here, you see this. For example, U. du by dh, du by dy, let us say. What is this quantity? Can you think of this? U in the y direction change. So what is its y direction? What is this du? U change. That means you are looking at, for example, here. Okay, here to here. What is its change? Okay. So here this is on top. You have a u, capital U. Inside it is like du. This is your du. Okay. This is not du. So here u, this is 0 here, and this is u. That is u plus delta u, right? Let us say here initially some u, okay, and here it comes u plus delta u. So it's basically du. Yeah, that is your du. And what is its change with, for example, here y direction? So this is little bit, right? There is a change here. So this is delta y. This is dy, and this is du. So that change. So you go from this to this. There is a small. There is a velocity. That velocity is actually it's increasing here. So that change of velocity is basically is again here some kind of u by h type only. If you think that h is very small, u is that you can think that inside that u is approximately close to the actual u. So what you are getting is this u by h is nothing but du by dy only. Okay. Imagine that you are looking at du here, and this is your h. Y is your h itself. Then that divided by this u divided by h is nothing but rate of change of the velocity u with respect to y. Okay, not rate of change. So u change of u, derivative of u with respect to y direction. So this u by h, whatever you are writing, no, rate of angular deformation is nothing but rate of strain. So this is actually rate of strain. We say that is your du by dy. Why rate of strain? Rate is because u, that is the velocity, dx by dt, no? So dx by dy. So rate of strain in that too. As you look at y direction, there is a small change is happening, no? So it goes like this. So here, if you look at the here and here it is more, here it is little less. So the difference is basically the du, and that this is the direction dy. So the dou u by dou y is basically rate of strain. This is your du by dy. Or if you actually think that h is very, very small, u is that capital U is this one, then u by h is also, they both are same. Okay. So this is what you have. So this implies that tau, whatever you have, that shear stress is actually mu times u by h is like du by dy. So this is exactly what you get. So this is actually nothing new. So you have a shear stress. Shear stress is proportional to mu. That's what you are saying. So this rate of strain or rate of angular deformation at the, with that rate of strain, any fluid will have certain things, no? That this is fixed, dou u by dou y, those kind of things. In that direction, it is fixed. Okay. Any questions here? Are you following? Respond, please.
Yes, sir.
Yeah, see, we are only looking at one direction. So in general, for the real fluid, you may have all the different directions. This rate of deformations, you may have to look at it. That is what we do for when in the derivation of those Navier-Stokes equation, equation momentum. No, that is the time you do this one. You basically shear stresses are proportional to the rate of strains here. For example, there is the difference between fluids and solids. For solids, you do basically shear stresses are proportional to strains there, only strain. This is for solids. Okay. So in fluids, what is the main difference with fluids is this is actually proportional to strain rate. That's what you are observing here. So dou u by dou y, for example, is just part of it. Because only we are looking at the simplest flow, no, unidirectional flow. So flow dimensionality, you say, for example, here only one direction only we are looking. Fluid can go all directions, no, all three directions. So we are looking at the simplest case of going unilateral, unidirection, x direction only. That is why we are getting part of this whatever strain rate, which in general for real fluids. And here we are only looking at, in our situation, this is basically, this is your constant mu. If this is your constant, basically this is proportionality constant, or if it is linear, okay, it's basically linear. So this is fixed now. So this deformation is fixed for a given fluid, okay. So whatever shear stress is applied, that is shear stress, and you draw this one. So the mu looks like linear, okay, or it can be constant also. Basically constant, okay. Newtonian fluids, basically that's what they say. So you have uh, shear stress, and this is actually proportional to rate of strain. Rate of strain. So how do you plot this one? Let us say mu. Okay, this is mu. Mu is basically okay. So if you say a strain, okay. So okay, so I'll not confuse you. So let's do this one. Exactly, I don't remember also. So in any textbook, you see that generally it is written this fluid mechanics. Okay, so this is actually linearly. This mu is linear. That is what is the Newtonian fluids. Okay, so for non-Newtonian fluids, it won't be like this. It will be non-linear curve. So that is the reason we say that this whatever you just now define, no, this viscosity. Now, for Newtonian fluids, that is the Newton law of viscosity. That is, shear stress is proportional to the viscosity at the given rate of angular deformation. Rate of angular deformation or strain rate. Okay, strain rate, given a strain rate, that's what happens, and shear stress is proportional to mu. Okay, that's what is uh, this one. Okay, so maybe, oh, I think I misplaced this one. So this this page I added in between. So whatever we taught yesterday, it is here. So anyway, I'll try to modify that one. Okay. So we'll cut and paste maybe later on. Okay, don't worry. We'll go to the next. So that is what is your uh, viscosity, right? So mu is called the viscosity. Viscosity. It can be constant for certain fluids. Okay. So it may be varying with space and time. Okay. So mu is actually depending on all this is a fluid property. So it depends on all the spatial variables and time t. Okay. So we'll see when we do this dynamics, no, fluid dynamics, exactly how we are going to do this one. So the first we finish this viscosity. The second one is so if you look at this viscosity, now you keep remembering this situation like F mu is actually, if you rewrite F equal to mu times AU by H, no? So mu you can write it as HF divided by AU. So you can write its units. Okay, so what are the units for this? Units for mu viscosity units are what? Can you give me this one? H is length, A is area, L square. Okay, this is force, L by L square. What is U? U is L by T, right? L by T. So L cancels, T by L square, force T by L square. So that is why they generally write Newton, force is Newton second, Newton seconds per meter square. Okay. So this is your viscosity units. Viscosity unit. Okay. So viscosity, if you write it, so you do that one. So some textbooks, they may say there's something called kinematic viscosity. Kinematic viscosity means basically nu, you write it as nu, which is mu divided by the fluid density. Whatever, so fluid properties, what we discussed is rho and mu, right? So far. So if you take the ratio, that is actually kinematic viscosity. This is your dynamic viscosity. Mu is actually dynamic viscosity. Then you say this one. So if you use this one, so what you have here is FL divided by L square L by T, and divide by, this is like M, no? Rho is M by V, so L cube divided by M. So you can cancel now. So this will give me FL by F by FL by FLT by M, right? FLT by M. So what is this one? But F by M, that is F equal to MA, no? F by M. MM cancels MA square. This is like F by M acts as acceleration, right? So this is like meter per uh, second square, right? Meter per second square. L is, LT is what? So this is like L meter per second square. This is L is meter, one more meter, and this is T as second. So 1 second cancel. So finally you're getting meter square per second. So this is your unit for kinematic viscosity. So meter square per second or Newton second per meter square for both dynamic and kinematic viscosities. Okay, this is one of the properties. Just try to understand and just leave it there. Okay, so you don't really you don't have to. So you just need to understand, because we are dealing with these fluids. Sometimes when you are reading, it should not confuse you, even in the among the textbooks. So you should understand, and just not much mathematics. It's just basically physics. Okay, so non-Newtonian fluids, as I told you. So this is not the case. Newton law of viscosity fails. So there you may have a different kind of relation. For example, the type non-Newtonian fluids. For example, tar or molasses, you can think of non-Newtonian fluids. So actually, non-Newtonian fluids, we don't give that earlier definition, no? That you give apply the shear stress, it's actually proportional to the viscosity. That is the definition that we give. Newton law, that is actually Newton law, right? What is that definition you have given earlier? Where did we write? We wrote it here, right? Yeah, today we wrote it here. Yeah. So this one. So the original one that we have given, no, the property of the fluid that gives the resistance to shear stress. That itself you give as internal friction, no? That you give it as a definition. If you for non-Newtonian fluids. Okay. So there are certain fluids. If you look into advanced textbooks of fluid dynamics, there are some. It follows tau proportional to this shear rate. That's what you found, no? This actually power something. It's a power of shear rate. If you do, those are called power fluids. Okay, power fluids. Those are non-Newtonian, but they are called power. At this rate, if you assume, those are called power law fluids. This is called power law. So basically, you are assuming that it follows like this. You are seeing, no, shear stress is actually proportional to rate of shear for the Newtonian fluids. Non-Newtonian fluids, it is not. It is not proportional only, you are saying. But then, if you assume that it looks like, as a power of shear rate, if it is there, those are all your called power law fluids, power fluids. Okay, and certain fluids follow this one. So that is the reason you may find these fluids. Those are also part of non-Newtonian fluids. Okay. So what are the other properties that we see of the fluid? Are basically thermal conductivity. It's the temperature, thermal conductivity. This is also something similar to what you have done just now. So you have
Sir,
a heat. Yeah.
sir, what are
Hello.
the real examples of non-Newtonian fluids, sir? Real
Non-Newtonian is
life
like a
examples.
tar, molasses, something which is sticky, gooey. Okay, those are which moves very slowly.
Okay, sir.
See, for
Okay,
tar,
sir.
no, tar is the best example. Okay,
Okay, sir.
highly viscous, and you try to hit hard, then you cannot penetrate it. Slowly you enter slowly, you will see. You might have seen
Okay,
some
sir.
pictures now. So if the non-Newtonian fluid is where it is not following that law, it's not proportional to viscosity, is not proportional to the shear rate. I mean shear stress. That is the only thing. Okay. So when the fluid is moving, that is already there is a fixed deformation rate. So that shear stress is proportional to the mu. Okay, in the Newtonian fluids. If it doesn't follow, you say that it is non-Newtonian. Examples are tar, molasses, those kind of things. Some sticky, heavy kind of fluids, those are usually non-Newtonian. Okay.
Okay, sir.
For example, ink. If you see, in the printers, that is also non-Newtonian. Okay. So here
Okay, sir.
also you have this another property of the fluid, thermal conductivity. So just like your this thing, so you have you would denote it as some kappa here. Okay. So some thermal conductivity kappa. Uh, okay. So this kappa is how you do is there is a heat flux. This is by Fourier's law suggests Fourier's heat law of heat conduction. Okay, Fourier heat law is suggests that heat flux. This is basically, see, what is heat flux? Basically, heat is like something which you cannot measure. It's a quantity. Okay, it's a quantity that you cannot measure. So non-measurable, right? For mathematics, if you mathematician, you think that heat is something, it's very hot. Okay, it's not quantified. Okay, it's non-measurable. So, and what is the equivalent thing that you do with respect to heat? That is temperature. You can measure it, right? This is quantitatively you can measure it. Measurable quantity, non-measurable quantity. Measurable, non-measurable. So that's what. So heat flux, the amount of heat that you enter, right, for a plate or something, or in your fluid. Right now we are only dealing with the fluids. So this is actually proportional to rate of change of the temperature. If you call this T and here you call it T. Okay. So unit time. So this is basically, so this is Q is heat, and if you say dq by dt. Okay, dq by dt. This is proportional to, is actually that thermal conductivity, that proportional constant. That minus sign is because heat flows from hot areas to hot temperature to lower temperature. So that is the reason you give. This is like dt by dy. Dt by, in our exactly our situation, that dy n. Okay. So that is rate of change in that direction, the y direction or x direction. In our case, you can think that is x direction. Just now we have seen some. So this is simply, it doesn't matter, some direction. In x direction, rate of change. So dt by dx is change of t in x direction. Something similar to viscosity. So this k is something similar to viscosity with a negative sign, because heat is actually the flow is actually going from hot side to cold side. That is the reason we, in the heat conduction problems, you use this minus sign. Okay. So this is one simple property. Okay. So there is something called something similar is diffusive constant. Okay. Diffusive constant, diffusivity, here we talked about heat. Here we use mass diffusivity. Something, for example, in a water you throw some ink. Okay, so it diffuses, right? As you see, it spreads. So that spreading is basically, it will have some constant. That is also some law. We don't need to worry. So there is also property of fluid if you are dealing with really some advanced fluids. Okay, so just that is one. And what are the other properties that we can think of is the density, that we already talked about it. Density, and what else? Pressure. The pressure also Pressure is basically fourth one. This is the fourth one, and this is fifth one, sixth one. If you think of as property, and you say that pressure and surface tension, we already talked, right? Surface tension. Surface tension. Surface tension, what is surface tension? Something, it holds, you shear, normal stresses won't be there, and you don't consider, on a fluid element. So what are the forces are there? Only shear forces act the surface between different fluid surfaces. This is one fluid, this is another fluid. For example, this is air and this is some soapy water. Then you have only deformation, only shear forces only will act. There is no normal. Normal forces won't be is balanced. Okay, balanced by these shear forces. That is what is the surface tension. Pressure is something on a surface element, unit area. What is the force acting perpendicularly? That is your pressure. So this is basically normal stresses. Normal stress. Normal stress means force per unit area, F by A. Okay. Shear stress is also for F by A only, but in the horizontal direction. That's what you have to understand. Okay. We'll just go like this. So this is for liquids, right? Incompressible fluids. Compressible also, for compressible fluids like gases, you also have something called compressive forces. Okay. Compressibility constants. With some compression, if quantified, that is called compression. So just like you did for some fluids, for gases, you can give how much you can compress it. Compressibility constant. Okay. So compressive forces, exactly how much compressive forces. Okay, so what you do is you apply some compressive forces. So we'll just leave it here. We may not use it. These are the all possible compressive forces. Forces for gas fluids. There is also kind of, it's a property of the fluid. Okay, so we just leave it here, and also of course you have a temperature. Temperature is also the property of the that those things that physics we will not worry too much. So these are certain properties of the fluids in general. And now we can just think of certain flow properties. So what we have is different flows. Once you give this shear stress, you apply shear stress, and the fluid starts deforming. A rate of deformation depending on, so it will form. So that is depending on your basically your viscosity of the fluid. If there is no viscosity, it simply whatever starts, it will going like that. It will never stop. Okay, the rate of strain will be constant throughout. It will be there like that. So because, right, so shear stress you apply, so it is whatever shear stress you apply, that continues to be there as a rate of strain. It will be just going. That is the reason at the boundaries it won't stick. There is no internal friction for ideal fluids. That is why you simply allow that horizontal velocity, whatever the fluid velocity will be there, you have to take at the solid boundary. Okay, for ideal fluids. But for that's why you say that that's a slip condition. Okay, for ideal fluids. For real fluids, because of this internal friction, this viscosity, you basically have no slip condition. Velocity eventually has to be zero at the solid surface. For example, this is a solid surface. At here, velocity is zero. Horizontal velocity has to be zero. No slip condition. Okay. So given velocity, given viscosity, you may see that this rate of strain or deformation, rate of deformation may be changing. So that is only the amount, but certainly some amount will be there. Okay, because the actual definition of your fluid is something. You give any shear stress, basically there is a fluid is moving. No, that is what you have given. Or however small you give, there is a deformation. No, so the only rate of deformation, that exactly the amount of deformation may be varying, but for fluids, it's always the case. Okay. So now we can look at the flow properties. Okay. So properties of flow properties. Flow properties. Now we have a flow property. What do we say? What is the flow properties? So that basically Once you start deforming, that's we say that is actually moving. The fluid is moving, it's deforming, and that is what is the flow. We call this, that's a flow, deformation of the fluid. Okay, deformation of the fluid is called the flow of the fluid. Okay, so what type of properties that we have here is one is a steady flow. Steady flow is something which does not depend on time t. Okay, and then other one is unsteady flows. Unsteady is just opposite. Unsteady. Unsteady flow is basically it depends on time. Also called transient flows. Okay, so this is called unsteady. Are you following?
Yes, sir.
Yeah, another property of flow property is basically just now you have seen some example where you move the plate only in one direction. So, but it is actually three-dimensional fluid, but you looked at only one direction only. So that is called flow dimensionality. Flow dimensionality. Okay, sometimes you may look at only two-dimensional flow. Sometimes you may look at actually it is three-dimensional flow fluid which is flowing, but only certain directions. If you look at you only that is the flow dimensionality. If you see in the textbooks, that is the flow dimensionality you say. Okay, so and what are the other things that you have? Uniform flow, uniform and non-uniform, uniform and non-uniform flows. So here the problem is with the uniform is uniform means it doesn't change. So u, v, w, these are the velocity components of the flow, doesn't change. They do not change with respect to space. Then you say it's uniform. Okay. So I'll try to, if it changes, it is non-uniform. So let me give you exactly some picture so that for you to understand exactly what is the meaning of uniform and non-uniform. Between the plates, let us consider the same situation what you know just now. So this is the between the plates. If you just go with this same velocity, okay, this is uniform. Okay, but as you know, as you go, it is also with time. Okay, so it is only at different at fixed time, different time, fixed time, fixed time, fixed t. You fix your time once you are in the flow, so you see that the velocity doesn't change. Now you try to consider this one, this type of situation. Fluid is going like this. Initially, you have a temperature like this at this place, and slowly it's increasing. It's increasing here. Okay, let's give bigger arrows here. It's increasing, and you have a flow, different flow, right? So you'll have more arrows here. So it's increasing, no? As it accumulates a smaller hose, no? Here this end. So it slowly it increases. So this is kind of non-uniform. Non-uniform. You may see that locally. You may see that here. It is locally at this place. It is locally uniform. Locally uniform. In the y direction, it is locally uniform flow. Okay. So this is one type. And what else we have is 4 we wrote, right? So this is 5. Let me put as 5. Rotational and irrotational flows. Rotational and irrotational flow. Irrotational flow. So what is the meaning of this? Rotation means you basically now you have flow vectors, right? So you have always a flow means it has certain velocity. Deformation means it goes with some velocities, right? UVW is your velocity component. Okay, velocity vector. Velocity vector is UVW. Then for this, if you take it's a vector field, no? At different places, different vector. So it depends on it depends on the u, v, w depending on x, y, z, and that's your position and time, x, y, z, and t. So this is your velocity. U, both capital U is a vector that depends on the velocity, depends on the spatial variable x, y, z, and t. So if gradient, this you know the meaning, right? Gradient, dou x, dou y, dou z. This a cross product with this vector. If this is equal to 0, then we say that it's irrotational. Then the flow is irrotational. If it is not equal to 0, del cross u is not equal to 0, then flow is rotational. Flow is rotational. In that case, what we do is we will define something called vorticity. So the W omega, we write it as omega. That is by definition, this is a gradient cross U is called vorticity. Vorticity, that is that no rotational quantification of the rotational. Okay, it's a vector, it's a vorticity vector. You define like this because there is something called vorticity lines, just like streamlines that we talk about in future. So we'll see. So these are the different kinds of flow properties. Okay, just try to understand, that is enough. Okay, so you don't worry too much about it. So and in each situation, whatever we deal, no, so we will try to recall so that you get familiar with these things. Okay, so I'll stop here. Any questions up to here? Yes. Hello. Any questions up to here?
No, sir.
Yeah, fine. So if you don't have questions, you can leave. Let me know if are you following first of all? Can you respond?
Yes, sir.
Okay, so see, this is not for the exams. I'm not. It is not like you're learning for exam. These things is like fluid. Fluid means you are understanding the fluid. What type of things are there, and then we do exactly what else we do is basically how do we study? How do we dynamics? How do we study? There are some approaches. So with that, basically calculus. What we are doing is nothing but calculus. What we do mathematically, calculus we do, and we try to derive those equations. What are the equations that can govern the whole flow? Okay, in general, are simpler flows. How the equations are simplified? Can we give the solutions? Can we talk something? Can we give some implication? This is what we do. Okay. So for that, you need to understand exactly fluid properties and flow properties. Of course, we see if you include all the fluid properties in your fluid, it's very difficult. Sometimes you may not know the physics. For example, diffusive thing, for example, you may not understand. Many physical processes you may not understand. If you understand simpler situations like viscosity, that is good enough for the course. In future, if you are working in some standard fluids where you need this temperature and also diffusivity, that time you can, that is just a fluid property you include. So that physics you need to understand and then try to work. Okay, this is how the fluid mechanics work. Okay, so anyway, I'll see you next class tomorrow. Tomorrow at 11, we'll see.
Okay, sir. Thank you, sir.
Yeah.